Let's take a look at how to do problems where we have two samples with paired matches, meaning like sample one contains husbands and sample two contains wives, or mothers and children, or perhaps a before and after situation. So what we end up doing when we have a paired match is, rather than actually working with two different samples, we basically take the difference between each of the pairs in the samples, and we work with one sample containing the differences. Now, that doesn't mean that we'll only be given one sample. For instance, in this problem, we have a set of 5 temperatures at 8 a.m. and a set of 5 temperatures for the same 5 subjects. These are body temperatures, not outdoor temperatures, at 12 a.m. In order to get the mean of the differences, D bar, and the standard deviation of the differences, S sub D, if I load this into StatCrunch, let me get this where I can see both screens at the same time. There is, under T-statistics, a way to do paired data. However, this will not give me the standard deviation of the differences. It'll give me the standard deviation of each sample individually, but to get the standard deviation of each of the differences, the only way I can do that is to actually get the difference between the two elements in each pair, and then go ahead and run my summary stats on that. So if you'll come up here to data, we want to go to compute an expression, build, and we want to do the elements in the first column minus the elements in the second column, right? So I'm going to highlight, I'm going to click on the first column, add column. Then I'm just going to say minus. I'm going to click on the second column, add column. Okay. Compute. And it has added a new column to the data table, which contains the difference. Now, if I do my summary stats in a column, and I really only need the third column there that I've just created, I want the mean and the standard deviation. I'll just go ahead and pick up the variance as I go. So the mean of the differences is negative 0.36. The standard deviation of the differences, 2 decimal places, is going to be 0.48. What does mu sub D represent? Mu sub D would hopefully represent the population mean of the differences. So the mean of the differences from the population of matched data. Nice work. Now, to set up this as a hypothesis test, I don't need the standard deviation because StatCrunch will go ahead and calculate it for me and just use it. I don't have to report what it is. I still will need to load these into StatCrunch. So the following data lists the ages of a random selection of actresses when they won an award in the category of Best Actress, along with the ages of the actors when they won in the category of Best Actor. The ages are matched according to the year that the awards were presented. They have to be matched up in some logical fashion. If you simply have a sample of the ages of the actresses and an unrelated sample of the ages of a bunch of actors, that is not a matched pair. So use the sample data with a 0.01 significance level to test the claim that for the population of ages of Best Actresses and Best Actors, the differences have a mean less than 0. If the mean, if the actress's age minus the actor's age is less than 0, meaning that's negative, then that means that the actress's age would on average be younger than the corresponding actor's age, right? So it's indicating that the best actresses were generally younger than the best actors. In this example, mu sub d is the mean value of the differences d for the population of all pairs of data, where each individual difference is defined as the actress's age minus the actor's age. The null hypothesis will, of course, be with the equals. So the null hypothesis is that the difference between the two is 0. The alternative hypothesis, our claim is that the difference is less than 0. So we'll say literally mu sub d is less than 0. That's the same thing as saying it's negative. Make sure you do not round off your 0. Okay. Now the test statistic. Let's go into stat, t-stats, paired. Column 1 is the actress. Column 2 is the actor. The hypothesis is going to be equal 0, or make sure you set this up right, less than 0. Compute. So our test statistic here, negative 2.29 would round to 30. The p-value, 3 decimal places, is going to be 0.024. Since the p-value is, now we were comparing this to 0.01. Okay, this one's a very low significance, or very, very high significance, really. The p-value in this case is going to be greater than the significance level. Therefore, we will fail to reject the null hypothesis because there is not sufficient evidence to support the claim that the actresses are generally younger. Now, if this had been 0.05 significance level instead of 0.01, we would have actually supported that claim. But because they chose to go with 0.01, then it was actually, even though it was pointing in the direction that the actresses were younger, because of that significance level, we will fail to reject the null hypothesis. Now, confidence interval. Let's go to options, edit, just change this to the confidence. Because this is a one-tailed test, we need to go with 0.98, double the alpha value so that you've got that much at each end. If it's a one-tailed test and you're changing from a hypothesis to a confidence interval, double the alpha. We want to compute that. So the lower limit is going to be at negative 21.6. Upper limit is 2.2. Since the confidence interval contains 0, although only barely, we fail to reject the null hypothesis because that means the difference is 0 or could be 0. That's how you do this. Let's look at one more problem because this one's a little different. Several students were tested for reaction times in thousandths of a second using their left and right hands. Each value is the elapsed time between the release of a strip of paper and the instant that it's caught by the subject. Results from 5 of the students are included in the graph to the right. Use a 0.20 significance level to test the claim that there is no difference between the reaction times of the left and right hands. Now, so we've got our graph. We can see that it's more or less in something of a linear fashion here. So if we load this data, I click this icon up here. If we load this data into StatCrunch, don't need this now. The hypotheses, let mu be is it the mean of the differences or the difference between the means? Are we getting the average of the 2 samples and then subtracting that? Or are we getting the average after we have subtracted each pair? That's it. It's the mean of the differences. For the hypotheses, of course, the first one is equals. The second one, because the claim is that there is no difference, is going to be the claim that there is a difference. So that's simply a not equals. Now the test statistic. Come over here, t-stats, paired. Put in our data columns. Make sure our hypotheses are right, compute. So the t-statistic here is going to be negative 5.573. Now, this asks for critical values. It doesn't ask for the p-value. The critical values are those values which we compare the t-statistic to. The critical values are the values that separate the area in the curve between which we would not reject the null hypothesis and we would reject the null. To find the critical values, we need to go into calculators. These are t-values. To do a t-value, you have to put in the degrees of freedom. We have 1, 2, 3, 4, 5 data elements, so the degrees of freedom is 4. The critical values are based not on the sample, but on the significance level. The significance level, when you're finding a critical value, is split between the 2 tails. So for a 0.20 significance level, we're going to have 0.10 at both ends. And if we're going to leave this at just a less than or equal to, we can put in the 0.10. So 10% is going to be below negative 1.533. If I copy this, just to make sure I've got it, if I change this to between and put this in both ends, and then I'm going to take out the negative up here, just to illustrate. We don't need to do this, but to illustrate, notice that this has 80% between the 2 cutoffs. Therefore, we've got 10% at each end. So that confirms that this is going to give us a 20% significance level. So the critical values, they do have one here. It's got equals for 1 and then plus or minus for 2. We're doing the plus or minus with 2 critical values because this is a 2-tailed test. And it's not going to make us put in both the positive and negative. Let's see, 3 decimal places, so 1.533. Fantastic. And then I'll let you reach the conclusion from there.